One challenge with building decision trees is that if we don't stop growing the decision trees, they continue to create more and more partitions and get overly complex. Decision tree models can create overly complex trees that fit the training data almost perfectly, which may end up being a bad thing. Here's a decision tree that can get a training accuracy of 0.93. And the way we can test that the decision tree is overly complex is that we can look at its performance on another set, here the holdout test set. And we can see that this model doesn't do well on the test data. This is called overfitting. The model fits the training data so closely that it doesn't generalize well to other samples or the real world. We can look at the difference in the training and the test accuracies to determine whether overfitting is an issue even on high-dimensional data where we won't be able to see the decision boundaries. One way that we can combat overfitting is to control when we stop growing the trees. We can stop growing decision trees by setting the maximum depth a tree can grow to. In this particular example, when we have the max depth of 22, which is the default, we get an overly complex tree that achieves a high train and a low test accuracy and overfits on the data. But if we control the max depth to say 4, then we get a much simpler decision tree, which gets a training accuracy which is similar to a test accuracy, which is greater than the test accuracy that we see with the overly complex tree. We've seen how we can use max depth to combat overfitting. Another popular way to combat overfitting is to build what's called a random forest. Random forests construct multiple decision trees and average their risk predictions. So for a patient, we might have each tree come up with a prediction of risk like 20%, 50%, or 10%, and the random forest takes the simple average of those risk predictions to arrive at a risk prediction of 15%. So how can a random forest be trained? There are two key concepts in the training of a random forest. First, each tree in the forest is constructed using a random sample of the patients. For instance, for the first tree, we might draw P1, P2, P1, which can happen because the random forest samples with replacement. Second, the random forest algorithm also modifies the splitting procedure in the construction of decision trees such that it uses a subset of features when creating decision boundaries. With these two key concepts, a random forest algorithm learns to build multiple decision trees on given data. Random forests generally boost the performance over single trees. So with a single decision tree, we might get a test accuracy of 0.71. With a random forest, which consists of 100 trees, we get a higher test accuracy. Random forests are called an ensemble learning method because they use multiple decision trees to obtain better predictive performance than could be obtained from any of the decision trees alone. There are other popular algorithms that use ensembles, including gradient boosting, XGBoost, and LightGBM, which are also able to achieve high performance when working with structured data in medicine and in other domains.